be safe on the tour. When you walk around, you're going to find out that this is an industrial site, that there are rails sticking out of the ground, there are gopher holes that are here, and some of the material is dilapidated. If it's in too bad a shape, we've marked it off and we don't want you to go there. But otherwise, please stay on the paths that we have for you. It's steel. So what they do, they take iron and then they burn it further to get more of the carbon out of it. And then they add alloying elements like tungsten, titanium, molybdenum to make it stronger, corrosion resistant, etc. And that's when you have steel. Carrie Furnace was part of U.S. Steel's Homestead Works. Homestead Works was a fully integrated steel complex. That means they made everything from iron all the way to the finished products of beams and extrusions and castings. Homestead Works had 15,000 employees at their peak, and Carrie Furnace had 3,500. So 3,500 people worked here, worked around the clock, 24 hours a day, 365 days a year. At its peak, Carrie Furnace had 5 blast furnaces that were operating. Only 2 furnaces remain, Furnace 6 and Furnace 7. This is the blast furnace, as you see it on the left side. In the middle are those tall cylinders with domes on them. They're stoves. The stoves heat air that gets fired, blasted, into the bottom of the furnace, and that's why it's called a blast furnace. So you heat the air in the stove and then fire it to the blast furnace, and you can barely see the top of the other furnace on the other side. That's what we're going to see up close today. I'll give you a quick overview of my background. I was born and raised in the Monongahela Valley. This is the Monongahela Valley. It's the area around the Monongahela River. In the Monongahela Valley, when I was growing up, 7 out of 10 families had somebody working in the steel mill. 7 out of 10. So everybody knew somebody in the steel industry. I had 2 grandfathers, both immigrants, that worked at U.S. Steel. It was Carnegie Steel at the time. They each worked more than 50 years. So my 2 grandfathers worked more than 100 years at U.S. Steel. My father broke that tradition by becoming a school teacher, shame on him. When I got out of high school, I would work my summers in the steel mill, and he really wanted to do that. So in high school and then in college, you would work in the steel mill because you'd make enough money to pay for your tuition in college for the next year, and he actually did that. So I was a member of Local 1397, a card-carrying steel worker for those 5 years. And then I graduated from college. I went to the Army. When I got out of the Army, I applied for a job at U.S. Steel as an industrial engineer. They hired me and assigned me here at Carrie Furnace. So I worked here at Carrie Furnace as their industrial engineer, and I also worked at Saxonburg Sinter plant. It's 37 miles north of here. They take dust out of the furnace and they burn it into a solid material to make what's called sinter, and then they would recycle that back into the furnace so they can get the iron out of it. I worked here until 1975 when I graduated from law school. I went to law school while I worked here, knowing I didn't want to work here all my life. When I graduated from law school, I got hired by Alcoa, so I shifted from the steel industry to the aluminum industry and worked for Alcoa for over 30 years. Alcoa put me in a number of positions. They hired me as a patent attorney, then I ran the patent department, the general legal department, I ran the procurement organization. I was their auditor. When I knew Control-Alt-Delete, they made me the CIO of Alcoa, which was interesting. They gave me lots of different experiences. I ran environment, health, and safety 3 times under 3 different CEOs. And then it moved from there. It moved south and it moved west. The coal mines were in the Pittsburgh area, and that was the fuel for the steel industry. They also had abundant water, not for transportation, for cooling. U.S. Steel used so much water that if they didn't put the water from the Monongahela back, the Monongahela would have stopped. That's how much water they used. They'd bring the water in, they would cool all the facilities that they had. They also had extensive rail networks. The rail networks were built in about 1850s, 1860s across the country, and they were built on level areas which were around the riverbeds. So around Pittsburgh, you had a lot of rivers, you had a lot of rail. They also had labor. The immigrants came to Pittsburgh because there were jobs here. And there was a lot of immigrants here and a lot of people that could work. And they had rich industrialists, people like Andrew Carnegie, J.P. Morgan, Henry Clay Frick, Charles Schwab, people who were willing to put their money into the industry and let it flourish. Lots of inventors were from the Pittsburgh area, and a lot of it was driven by industry back in those times. From Westinghouse, Hines, George Mesta, Henry Laughlin. Joseph Joy founded the underground mining industry, and you may have heard of Joy Manufacturing Company. Charles Martin Hall founded Alcoa, H.K. Porter, Coppers, Robertson, Babcock, Wilcock. You hear these names, they came from the greater Pittsburgh area. In 1900, Pittsburgh's East End, that would be this way of Pittsburgh, it would be Braddock and Wilkinsburg. It was the richest neighborhood in the world. Pittsburgh was the fifth largest city in the world, but it controlled more of the assets than any other area in the whole world. So Pittsburgh controlled 60% of America's assets in mining, steel, railroads, aluminum, food, glass, oil. Standard Oil and Gulf Oil were both founded in Pittsburgh, and banking. There was a train called the Iron City Express that ran from the east end of Pittsburgh to Manhattan every day. And some of those rich people would have their own Pullman cars, and they'd attach it to the train. They'd go up and back daily to New York City. There was a brothers called Lewis and Charles Clark, who in 1897 built an automotive company. They built a car that was called the Pittsburgher. This is way before the Model T Ford. The Clarks actually patented the spark plug and sold that to Champion Company. The Clarks also lived on the east end of Pittsburgh. And it folds and it rounds itself off, and you can imagine about 100 of these with rounded off backs. It looks like a bunch of pigs, so that's why they call it pig iron. But they would sell that pig iron to Andrew Carnegie. Well, Andrew Carnegie wanted to own that facility, so he sent Henry Clay Frick to the Phones brothers and said, I want to buy that, and he did. He bought it for $700,000 in 1897. And that gave them the fully integrated mill. They now had the iron making facilities, but now iron was on this side of the river. Everything else was on the other side of the river. They had to build a hot metal bridge to take the molten iron across the river into the open heart. And you saw that bridge as you drove in here today. It was the longest span hot metal bridge in the country at the time. It's about 500 feet long, and they have to build it to withhold an awful lot of weight, so it's hard to tear down. So you get a lot of iron ore, and that has a lot of iron in it. It has about 60% iron in that material there, and that's why you get it out, and you want to get the iron out of that. They also took, the fuel was not coal. It was coal at the beginning, but then they found a way to get the volatiles out of the coal and make coke out of it. So if you had coal, you'd have about 60% carbon in it, but once you take all the volatiles out, you can get it up to 87% carbon. So coke, which would be this, and feel that, it's very, very, very light. And it took all the volatiles out, but it kept the carbon in. So you have 87% carbon in there. And when you put that in the furnace, that's going to be your fuel. And when you keep it heated and keep blowing the air inside there, that works. That coke came from Clariton, which is down the river, and it still comes from there today. Then you put in a flux material like limestone and dolomite. It's a material that causes fluidity in the material, and it pulls the impurities out of the iron ore and takes it into slag, which you pull out of the furnace at the end. Then you have to have air. You need air. You know how in the old fireplaces they use bellows, and you just use the bellows? Well, that's kind of what they have. So you heat the air to 1800 degrees in those stoves. You fire it into the bottom of the blast furnaces. In this furnace, there are 16 nozzles around the bottom, and the air goes into a bustle pipe above the nozzles and then into the furnace at 70,000 cubic feet per minute. That's like a cyclone. That's another thing I can't replicate. The air flowing around here was amazing. So you pull air through pipes like this over to the stoves. That pipe's 48 inches in diameter. It's a big pipe. And you just flow the air throughout the facility, and then you have to blast it into the bottom of the furnace. So the air going in the bottom keeps the heat going, lights up the carbon inside the coke, and then it causes the chemical reactions to occur. So all the material that got dumped into the top of the furnace starts to reduce, and you get the material at the bottom. You put 4 tons of material in the top, you get 1 ton of iron out at the bottom, and a half a ton of slag. Where's the other 2.5 tons go?
Yeah, that's a good question.
In the air. In the air. That's why Pittsburgh was known as the Smoky City. It was everywhere. It was terrible. Growing up in this area, you had snow that was gray, or reddish. Yeah, it was something. That air was everywhere. Most people who worked in downtown Pittsburgh would take 2 shirts to work, because by noon you had to change one. The other was just filled with soot. Yeah, it was something else. Okay, I'm for the tour today. I want to follow the flow of the material. The material came in by rail, and it would you had to take the material out of the rail and put it into a yard, and take it from the yard and get it into the top of the furnace. So I want to start where it came in. It came into a car dumper, and a car dumper took a railroad car and just turned it over. That's why it's called a car dumper. And just turned it over. Before that, you'd put 10 people in a car and they'd shovel it out. So they thought big. These industrialists, and you could think of picking up a railroad car and turning it over. So that's where we'll start. The car dumper is all the way down there as far as you can see. So we're going to walk past the furnace, and we'll start right there. And then we'll proceed to the ore yard. After it came out of the car dumper, they put it into the ore yard and made great big piles of material. So you'd have ore and limestone and dolomite and sinter and pellets. Pellets I didn't talk about. Later on, they found ways to take iron coming out of Minnesota, and they could pelletize it. So these would have a high degree of iron in them, like 90%. And then also imagine when you're putting all the material into the blast furnace, you could really fill it up really well and fill those nooks and crannies if you had this kind of consistency of material. So they were in there as well. So you have all these piles of material, and they have to be put into bins that got put into skip cars that carried up to the top of the furnace and dumped into the top. So we're going to follow that flow of material and then go to the bottom of the furnace at the end. Any questions before we get started?
You mentioned slag. Is
Yeah.
slag here? Where's the slag?
No, I don't have it. I'm sorry.
What happened to the slag? Where was it disposed of?
The slag was there was a lot of slag in the country, as you can imagine. Anywhere where you were making steel, there was slag. Slag was not any good. So what would you use it for? They used it for fill, mostly. So the biggest mall that was built in the country at the time was Century 3 Mall, south of Pittsburgh. And that's at a slag dump. It's where you would take the slag. The slag would travel, see that car there, the black car? That's a slag car. And you would take the slag car and fill it with molten slag and drive it out to the slag dump. And it was just south of Pittsburgh. And you would take, they would pull out 100 to 200 cars at a time. They would take them to the slag dump on the hill. And you can imagine if you have 10 cars at a time that you just dump them, the molten metal running down that hill. It was an event when I was a child. Your father would take you to the opposite hill. You would park there in the car and watch them dump the slag.
Wow.
And it's pouring out of 10 cars. It's like a firework display. It was wonderful. And then those 10 cars go away, and in come 10 more, and they do it again. And molten slag was all over the place. So they used it primarily for fill. They've tried it for agriculture because it contains some nitrogen, and it didn't work very well. And they use it as fill in cement. But they can't find a really good use for slag, and if you find that, yeah, there's a lot of it around.
Thank you.
Which is good. Thank you for that question. So it's filled with molten slag, and when you get it to the dump, you then just rotate it over, and it pours down a hill. This car dumper, and it would come in here and they would turn it over and dump it. From the car dumper, there was a transfer car underneath it that carried the material out to the ore yard. Then the man that ran the crane, or the person that ran the crane, would pick up the material from the transfer car and put it in piles. So if you looked at this ore yard, you would see piles of material 100 to 200 feet high, and there would be iron ore, pellets, sinter, limestone, dolomite, everything in here except coke. Coke came in directly to the top of the trestle that was up here, and the railroad tracks were everywhere. Of course, they've removed those. And this trestle that goes up there then would continue down, and there would be tracks everywhere. They moved the rails all over the property. Of course, there were no trees or foliage or anything growing in the ore yard. The ore yard's about 600 feet long, and nobody would ever walk through here. Very, very dangerous. You would just take inventory of the material from the trestle. The person that worked in the crane was busy all the time moving the material from the car dumper into the piles, and then from the piles up into bins that are behind that cement wall. Behind that cement wall is a row of bins where you keep respective materials. So you had all your different materials in the different bins. And then from the bins, they would go up to the blast furnace. They would go up in skip cars. If you look at that inclined plane, it looks like a funicular. There's 2 cars that are going up. They're called skip cars.
Okay.
The material goes in a skip car. One goes up, one goes down. It goes to the top, dumps the material in, comes back down again. So that's the way the material flows. We'll go up and take a look at the car dumper. Before we go up, I wanted to point out the hot metal bridge that you see in the distance. 500-foot long bridge. Every bridge in the United States has to have a name. The name of that one is Union Railroad Rankin Hot Metal Bridge number 35. Thought you'd want to know that.
Thank you.
It was built in 1900 by American Bridge, the heaviest span ever built at the time. There's only 7 hot metal bridges like that built in the United States. And if you think about it, it's a mistake if you build a bridge like that. You got to take iron from one side of a river to another. Why would you do that? Yeah, why don't you just build the iron facilities on the other side of the river? Then you don't need the bridge. But there were a lot of inefficiencies, as you'll see. I do want to point out there's many railroad cars down in the train yard at the very end of the property. This transfer car would drive down to the rail yard and pick up 6 cars. They'd pick up 6 cars and bring them all the way back, and they'd leave the 6th car on here and take the other 5 back. So you uncouple the 5th car from the 6th, pull them back, and then you're going to turn over the 6th car. Why would they do that? Why only 6 cars? Well, the reason is that's all that fit. There was a railroad track that went back here and stopped. How inefficient is that? Why wouldn't you build something that went straight through? I don't understand. They didn't own the property, I guess, but they should have found a way to make this a continuous operation. They didn't. So they had to get 6 cars at a time. You leave the 6th car on the car dumper. Okay, and now you're going to turn it over. And the way you do that, this entire contraption is going to rotate. First, the clamps come down on top of the railroad car, and that holds it down onto the track. Then you start rotating in a clockwise direction. The car is going to fall against that side of the machine. That's why you put boards over there to protect it from falling. There's 450 horsepower motors, that's all, that power this and turn that car totally upside down. And then the material falls down below into a transfer car that carries it out into the ore yard, and then that's going to get picked up by the crane operator. So that's the way it operates. That's the way it's supposed to operate. But in January, February, March, it gets kind of cold in Pittsburgh, and all this material has moisture in it. What does the moisture do? It freezes. So you turn the car over, nothing comes out. You bring it back down again, you put 2 people in with oxygen lances, and they burn the water to melt it so that you can then turn it over and burn it. When I worked here as an industrial engineer, microwaves were coming out. And I thought, boy, if we built a great big microwave oven, we could just get that done pretty easily. Well, they had a couple flaws. It would have burned all the hoses and lubricants and all the gears and things. So it had a couple flaws. That didn't work at all. But this was a very, very dangerous operation that they had here. Anywhere where you have rail, it's dangerous. Anytime you have that coupling, they have to open or close. People get inside there and they can get hurt. People would get hurt a lot on the site, but this was one of the places where they got hurt. In the early days, they didn't have any signals at all. So this guy driving a transfer car, he doesn't know, it's probably time to move now, and moves up ahead. So later on, they got smart enough to put in whistles and signals and different things like that. But a lot of people got hurt in the steel industry. From 1900 to 1910, they averaged 400 deaths a year at homestead works, just homestead works. Wow. That's more than one a day. Wow. And in the area, they had a distinct whistle of when there was a fatality. When someone was declared dead, there was a whistle that would go off. And you can imagine how the families felt in the whole area. They all come out at the end of the shift to see if their loved one comes out or not, their son or their daughter or their husband. It was different. But I've had the fortune to look back on industrial safety and have realized that it's the leaders that make that happen or not. If the leaders really care, you're going to get safety. If they really don't care, you're not going to get safety. If you look back on U.S. Steel's early days, they really didn't care. labor was almost fungible. You can go out to the gate and get someone else. So if this one dies, you just pick another one for the next day, which is such a shame. I had the fortune to work for Paul O'Neill at Alcoa. I was in charge of safety when Paul was there. Paul was in charge of safety. He talked about safety all the time. When he got hired as the CEO of the company, he was invited to New York City to talk about the company. So he goes to New York City, talked for 90 minutes, all about safety. That's all he talked about was safety, which is pretty interesting. So the analysts thought he was nuts. In fact, they said so. They said, sell your Alcoa stock. This guy's off his rocker. It's not going anywhere. That's all he cares about is safety. And people would ask him questions. So, why don't you tell us about R&D and about your acquisition plans and things like that? He said, no. He said, if we get safety right, we'll get everything right. And when Paul left the company in the year 2000, he became Secretary of Treasury under Bush. He was asked, were you a success at Alcoa? He was a resounding success. He quadrupled the revenue, tripled the income, stock split 3 times while he was there. He took market cap from 2.9 billion to 29 billion in those 13 years. It was incredible success. But his answer to that question was interesting. He said, if the lost workday rate and total recordable rate continue to fall, long after I'm gone, I will have been a success. He was there 13 years. During those 13 years, the lost workday rate, which is how many people out of 100 are hurt so bad they can't come to work the next day. Lost workday rate fell from 1.86 to 0.2. Fell every year, consecutive year for 13 years. How about that? And that was the leader driving that. And I've learned that it could be the opposite. If the leader doesn't care, it's not going to happen. So when Alcoa sends me to Russia, they average 5 fatalities a year at the plant I was running, which is terrible. You don't kill people in Alcoa plants. But I remembered I had a good leader and a good teacher in Paul O'Neill. He said if you get safety right, you get everything right. So I thought, we'll focus on safety. So we trained 8,000 people the first year, 6,000 more the next year, put people in protective equipment, brought in health and safety auditors. The first full calendar year I was in Russia, nobody died. How about that? They've now gone 8.5 years without a fatality in the Russian plant. Now that's some pretty good success. But it shows you what can be done. And I think at U.S. Steel, when they ran some of these facilities, they really didn't care until later years. And then it was the union that pushed for an awful lot of the safety and an awful lot of other improvements that they got along the way. And then when it became a partnership and management and union together wanted to be safe, you saw a lot of safety. It was pretty good. Any questions about the car dumper or the operation or the material that came in? Remember, we have 2 furnaces here. At the time when I was here, there were 2 more furnaces over here that were actually bigger than these. And they had their own ore yard, but this car dumper had to feed them as well. So this place was busy. It ran. And they were doing damage and other things. There were 14 trespass calls a week to the police. So when Rivers of Steel came, they first put a fence around the perimeter to try to keep people out. But then they contacted the graffiti artists. And they asked them, could we work with you? We'll give you certain areas and you can put the graffiti up, whatever you want. So this wall is the graffiti wall, and the graffiti artists come in regularly and paint something new. So about 2 months ago, they blacked out from the car dumper down to about where we're standing, and they just made it a black wall, and then invited the artists in to come in and paint whatever you want. So they did. They come in and there's a group of about 6 of them who decide who comes in, who paints where, and what they do, and they do it all themselves. And as we go down further, you're going to see some beautiful portraits that are down there. Rivers of Steel actually took one of an iron worker and made it their logo that came from the graffiti that's here. But what they get with that is they don't paint everywhere on these walls and on the furnaces and everything else. So it's turned out so far to be a pretty good partnership by working with those people. This gives you a good view of the furnaces too. Furnaces 92 feet high. The stoves are 104 feet high. This stack here had 75 feet removed from the top. It was a 175-foot stack, but they had to take 75 feet off because steel started to fall off it. Well, if you're a historical monument, you must return the place to its original condition. So there's a plan in place to replace that 75 feet over the next 2 years to make it look like it was originally. Okay, we'll proceed this way. Be careful what you're stepping.
Bill, do they ever have to do any cleaning in the interior of these vessels? Cleaning?
That's a good question. Not only cleaning. Imagine not only the interior, but the exterior as well. So The furnaces are made out of steel material that's 2.5 inches thick. These stoves are made out of material that's 1.25 inches thick. And then inside, you line it with a refractory brick. So there's refractory brick inside the entire length of the stove and the entire length of the furnace. They would wear out periodically. So about every 6 or 7 years, you had to reline the stoves.
Wow.
And about every 10 or 12 years, you had to reline the furnace and take all that refractory brick out. So there's refractory being used absolutely everywhere, all the time, by everybody. That's why the refractory industries grew up in Pittsburgh. Harbison Walker, H.K. Porter, H.H. Robertson, a bunch of them. But imagine all that refractory brick. So they would take it to dumps in the area, and they dump the refractory brick. In the Pittsburgh area, most properties are on hillsides. So if you owned a property like my father did, you had a backyard that had a hill on it. And most people wanted to build a retaining wall along the side of their backyard that had a hill. So what would you do? Dad would put you in the station wagon and you'd go out to the dump and get refractory brick and bring it home. And you'd do that 15 times. And if you go in the backyards of almost any of these homes here, they all have retaining walls in the back made out of refractory brick.
Cool.
Yeah, which was part of the industry growing into the neighborhood, which was interesting. If you look on the stoves, you see those diamond patterns that are on there on the side.
Yeah.
They're not decorative, they're functional. They're put at the junctions of the steel plates to hold them in place. There are 6 stoves up there. 3 are dedicated to one furnace, 3 are dedicated to the other furnace. And this gives you a good view of the skip cars too, going up the side plane. So the blast furnace itself is a frustrum of a cone. It actually comes out in diameter as it proceeds down. And you dump that furnace in the top. When the skip car goes to the top of the furnace, it turns over, it dumps onto what's called a bell. The bell is just a circular plate of metal. It dumps onto that plate. The bell drops and rotates and drops the material to another bell that drops and rotates. So that dropping and rotating actually mixes the material into a more homogeneous mixture as it gets into the furnace. Because inside that frustrum of a cone, you want the material to be homogeneous, so that when the hot air comes coming up through it, the chemical reactions can occur in a balanced way, and the iron can come out in a more efficient way.
Bill, what kind of temperatures were these operating at?
The stoves would heat the air to 1800 degrees. Okay. The furnace would fire the blast air in the bottom, and at the tip of those nozzles, which were called tweers, at the tip of that nozzle, the temperature would be 4,000. That would be the highest. And it would come out at about 28 to 3,000. When the iron came out, it was 2,800 to 3,000 degrees.
Did they
So
have
it's
to
hot.
allow for the expansion and contraction of the metal for those temperatures?
A little, but mostly these were constant. Yeah, these were always kept
always
at the
running.
always running, right? So you didn't lose a whole lot with that. But coming out, you had to account for that. Okay, we'll proceed in this direction. Cents an hour if you were a machinist or a blacksmith, that wasn't very good, but they were glad to have it. If you think about it, you can raise your family on that kind of money back in those days. But times changed. The union came by and started to put a little bit more pressure on the management to try to treat the employees more fairly. And if you think about it, the unions really drove an awful lot of the improvements in behavior and management that they really needed. The laborers were mistreated early on, and then they got the upper hand starting in 1934 to 1937 when the AFL-CIO was founded in the country, and they started to unionize the workers, and the unionized workers then started to demand more, and they were successful in doing that. Before that, there was a strike in 1892 at Homestead Works, and Andrew Carnegie got on a boat and went to Scotland because he didn't want to deal with it. He told Henry Clay Frick, you deal with that, settle that strike. So Henry Clay Frick, the way he settled it was to call out Pinkerton detectives. And the Pinkertons came in armed, and some of them went on top of the Boats building across the river, and from their perches on there, they shot and killed the steelworkers. And that doesn't help union management relationships at all. And it festered for quite some time. When I labored here in the late 60s, workers would even talk about that. Oh, remember when the Pinkertons shot some of us? Gee, even almost, 80 years later, they were talking about things like that. So it's incredible how that festered for so long. But then the unions started to drive better working conditions, safety, higher wages, and benefits. And benefits really started in 1959, when they had the longest steel strike in the history of the steel industry. It was 160 days, and President Kennedy had to jump in to stop that because they needed steel manufacturing to have the country improve. So he jumped in, forced them to settle. They did settle the strike, but that's when the union really started to demand more benefits. They demanded medical benefits, health benefits, dental, life insurance, pensions. And there was even one benefit that they got, that if you worked for the company for 10 years, you got 13 weeks vacation on top of your 4 weeks vacation every 3 years. And it was like an entity that people would talk about it. When do you get your 13? Yeah, I get mine next week, next year. When do you get yours? But the workers would do something with it. They'd take a family on a long vacation. They'd put an extension on their home. They'd put in their driveway or their front porch. They did things with those 13 weeks. But my thought was always, if they can do without you for 13 weeks, they can probably do without you. And that's when the pendulum started to push really pretty far. The steel workers were the first to get a lot of the benefits, which were probably reasonable for a while and then became unreasonable. And then the auto workers started to adopt all those same benefits, to the point that now when you buy a General Motors car, $6,000 of the purchase price goes to fund pensions of people who are retired on the price of a new car. Yeah, so it might just be a layer of oxidation. I can't think of any things that would happen.
That's why. I was trying to think.
So this is the stove area, 6 stoves, 3 for one furnace, 3 for the other. They would run the stove for about 3 hours, and then they have to shift over to another stove to run the hotter area in because it cooled off. So the workers would be back in these offices here with the gas rescue team. The gas rescue team would come out first, make sure the area is clear, and if it was, then the workers would come out and turn all the valves to turn off one stove and turn on the other stove. Very hot work and labor intensive. I remember walking through here, the radiant heat from here was so much, you always wore gloves, and you put your glove up so that the radiant heat didn't heat your face as you came through. Same at the furnace when you did that. But very hot conditions. A number of people that worked in here would stop at the meat market on the way to work. They'd buy a piece of meat. They would bring it in at lunchtime. You put it on the side of the metal, you heat one side, you turn it over and heat the other side. You can still order that in some Pittsburgh restaurants. It's called Pittsburgh Rare. It's singed on both sides, rare in the middle. Yeah, if you look, the conditions here are tight. I mentioned putting your glove up to your hand. Well, you can't do it when you get in here. You got to have both hands in the front. So it's really hot conditions coming through here. If you want, you can walk through and take a look at the areas there and get an idea of how close those quarters are. so you combust the air into the water. And they fed the air in before the
This looks like a hot job.
very hot. The place was hot. That's molten material. Yeah, of course, very hot.
Do you know what the life expectancy was for somebody who actually worked here prior to them buying?
It wasn't much. It wasn't much lower than national life expectancy.
Okay.
Not much at all,
Okay.
which is surprising.
Yeah.
But the steel workers, the coal miners, they were probably 3 or 4 years below the average because of what they breathed. Very, very tough. Okay, so we remember the material came in on the railroad car, went to the car dumper, got dumped, put in the ore yard. From the ore yard, it went in the stock bins. From the bins in the skip cars, dumped in the top of the furnace. So the top of the furnace is up here. It's 92 feet up above us. The material's in the furnace. It's working its way down. There's heat inside there that's supplemented with the blast of air that's coming in the nozzles. Around this hearth, there are 16 nozzles called tuyeres, T-U-Y-E-R-E. It's a French word that means nozzle, and it was a copper tuyere, the nozzle that was about this long and about that round, and the air would come from this bustle pipe that you see that went all the way around the furnace. The air swirling in there, and then it goes down through a pipe and through the nozzle into the bottom of the furnace. At the tip of that nozzle, the temperature in the furnace would be 4,000 degrees. And then it would work its way up. It would be a little less, but it would cause the chemical reactions to occur so that the iron comes out of the ore and the pellets in the center and comes into the bottom of the furnace. When it's at the bottom of the furnace, it accumulates and it starts growing up from the bottom of the furnace. At the very bottom, the furnace is 23 feet 6 inches in diameter, and the iron is accumulating in there with slag on top of it. And periodically, you got to get it out, or it'll keep accumulating. So about every 6 hours, they had to open the furnace. They opened the furnace at a tap hole. That's the tap hole. The way you open the tap hole is you get a drill. That's a drill. And you rotate it around. This is the drill bit. And you rotate it into that tap hole, and you drill through a refractory material, and the iron that's inside comes out. The way you would operate that, as soon as you see iron starting to come, get that drill out of here, or it's going to get soaked with iron and get destroyed. So they pull the drill out pretty fast, and out comes the iron. When the iron starts, it comes out a little bit at a time, and then it bursts through, and it explodes, and you see sparks almost the whole length of this cast ice. And it's something to see. It's beautiful to see something like that. But then the material starts flowing. The material accumulates in this area. The area is called a Baker Dam area because they want to dam the molten material so that the slag starts to float on the top of the iron. And then they open this dam on the side, and the slag can move in that direction into the slag ladles. Remember that black ladle that we saw over there? There would be a bunch of them lined up on that side of the furnace, and the slag would flow in that direction and go into the slag dumps. And whenever you filled one, you'd create a dam system to get it to flow to the next one and the next one. The iron would flow under the slag through these runners and into ladles that are down underneath us. We'll see a ladle later when we see that. But the material flows through these runners into the ladle down below, which is called a torpedo ladle, a submarine ladle, or just a hot metal ladle. And you'll see those down beneath us. Then when that ladle got filled, you would then divert the iron to flow in the other direction and fill another one. So you'd get between 200 and 400 tons of iron out of each cast. And then you have to plug the hole again. The way they plugged the hole was they would take a mud gun that would be on this side of the furnace. They would rotate it around the furnace. It would be full of a refractory material. There's a pallet of refractory material there. You can imagine there were hundreds of those laying around here at the time because you used so much of that refractory material. But they would rotate that mud gun in front of the hole and just fire a slug of refractory material into that hole, and it was so hot, it would solidify right away and plug the hole. Then you take the mud gun out and you're ready to clean up. The cast itself took about 40 to 45 minutes. Now it's time to clean up. You have to get all the slag out of the slag runners, all the iron out of the iron runners, and you dig that out with all the material and put all that scrap into this bin that's behind you. And that giant bin will hold all that scrap, and it can be downloaded so a truck can drive underneath that and you can just load the material into there and they can take it away to the dump. They would then line these runners with the refractory material. So you get more of that refractory material and just line all those runners so that whenever the iron comes out the next time, it doesn't destroy the runners that are there. So you're using an awful lot of refractory material. The cleanup took about an hour and a half to 2 hours, and when they were done, that's when they would take a rest or they would eat. When I worked here, I'd usually come out to see at least one cast a day, and I usually came to this furnace. And they'd usually tell me I had to go in this room here. And there was a glass there that you could look through and watch it. But the first helper that was here, he'd often come over and just close that so he couldn't see it. Nice guy, yeah. So I got to sneak out and watch the cast. But I remember the guy that worked here, all the people that worked here, they were big, they were strong, they worked hard. And the guy that worked here, the first helper, he'd hang his shirt on 2 hangers. He was that wide. And he was just one big man, but it was something to see. So then the iron comes out and goes into the ladles. It's got to get across the river, and it better get over there in 3.5 hours or it's going to solidify, and you don't want that to happen. And there's 4 furnaces operating when I was here. There's a lot of traffic, so we're moving slag, we're moving iron, and we're moving iron ore and coke in and out. A lot of traffic, railroad traffic. And if you remember that green map that I showed you at the very beginning, it was just full of track. That's because you're moving rails and the rail cars absolutely everywhere. But pretty interesting. Any questions about the casting operation? If not, I'd invite you to see where the tweers were, where the nozzles were. Yeah, so this giant pipe that goes around the furnace is the bustle pipe, and they take the air from the stoves and fire it into that pipe. It's swirling around there. When you walk through here, you can hear it, of course. And then the air escapes from there through this down pipe that goes into a hole in the bottom of the furnace, and there would be a nozzle there. Since that nozzle was made out of copper, you can imagine they're not around anymore, but this place would be lined with those copper nozzles everywhere. And copper has value, so of course you're not going to let it sit around after you shut down a facility. But those were the tweers where they were, and 16 of those around the diameter of the furnace.
Did women work on any of these jobs?
In World War II, a lot of the men went off to war, so they had to hire women into production jobs, and did.
Were they strong enough? And
They would be put in appropriate jobs where they could handle it. Most of the women went into labs, accounting, chemical processing, things like that. But some went into railroads, some became workers, and some became foremen.
so they actually worked here doing these jobs that required big men.
They did,
Okay.
but whenever the men returned from war in the 40s, they didn't want to work here, and most left. But about 10% stayed. And whenever I came to work then, if you found a woman, she'd probably be, then she'd be about in her late 50s, because she was hired during the war. You knew that they had worked through that time period, and they probably knew what they were doing pretty well, and they did. Yeah, they did. But you bring up a good point. How about other classes of people? Remember I said Andrew Carnegie built his first mill in 1875. That was 13 years after the Emancipation Proclamation. 13 years. Yeah, 13 years before he built his first mill, blacks were property. So were they discriminated against? Of course they were. And in the early days, they were discriminated against a lot, but not only them. There was discrimination in almost every class. And there were people that lived in their own neighborhood. So there were the Irish, the Armenians, the Germans, the Polish, the Hungarians. And unless you found a way to get through your group, you were going to be discriminated against. So it was a lot of discrimination throughout the industry. But blacks probably had it the worst. In the railroad, in the early 1900s, they published the wages of people on the railroad. So if you had this job, you got this much money. Unless you were black, you got half of that. You believe that? Actually published that. So that finally went away. And then in the 1930s, the AFL-CIO, the union, comes out and said, you got to treat people the same pay for the same job for same everybody, and they did. They put it into place. By the 1950s, it was pretty common that then no matter what class you were in, whether it was cultural, race, gender, didn't matter, you were getting opportunities to go into apprenticeships, to become plumbers, electricians, boilermakers, and you got those jobs. And when I reflect back on my life, the people who were fairest, fastest were big industry, because big industry really started to treat everybody fairly, I believe, and the military. And if you look at those two areas, I think they set the stage for let's do the right thing for the right reason, for the right people all the time. So it's good. So I think it's set a good stage. But if we also reflect on the industry, it's gone. Why is it gone? Why is the steel industry not here anymore?
Cheaper imports.
Steel isn't used as much.
Steel
Cheaper
isn't used as
overseas.
much. There's a lot of alternatives. For example, before 1963, every can for a beverage was made out of steel. Did you know that? Before 1963? To open that can, you needed a can opener. Yeah, but then the aluminum industry invented an opener, and now you can make that whole can out of aluminum and make it thinner than steel